we're going to be discussing memoization. So what memoization is a technique to reduce the time complexity of our recursive functions or our subroutines that break down into subproblems by caching intermediate subproblem answers. The reason we do this is we want to not re-express or re-solve a subtree of solutions that have already been computed. By reducing that recomputation, we change the asymptotic time complexity of our algorithm. What this code is basically solving is the solution to where we are is the sum of the two previous numbers. And these are the two previous numbers, n-1 and then n-2, the term right before us and then two terms before us. And then we keep solving, we keep recursing and recursing. And done this way, we're going to have a lot of overlapping subproblems. This is a huge key with memoization. If you see overlapping subproblems in the problem that you're solving, it is a good candidate for you to apply some sort of caching or memoization to speed up the solution, and often it will impact the asymptotic time complexity. Let's trace the recursive tree to see exactly what this looks like. Okay, n equals 7. What this asks us is, we need to find this subproblem answer. What's the answer to it? We want the sum of the term before us and the sum two before us. And now that we've decomposed it into these subproblems, we do the exact same recursive behavior. It eventually leads to the base cases. This recursion eventually pans out. If we draw the whole tree, something's going to become very clear to us. Again, in this example, n equals 7. And we're looking at the recursion tree and we've pruned out all of the exhaustive recursion here. The way the recursion would proceed is it would go depth first. We would first investigate the path of n-1, and then this subproblem would keep its state within its frame in level. It would investigate the next subproblem, n-1, n-1, which would go all the way down this right subtree. That's how it would go depth first, and then we would recurse back to this node right here. What can we notice here? The simple insight that we can have is that we're solving subproblems multiple times. The way the recursion goes is this way. We're going to say, what's the answer to the 7 subproblem? What's the answer to the 6, 5, 4, 3, 2, 1? What's the answer all the way down to this subproblem? And our base cases are the 1 and the 0. And what memoization aims to do is it wants to solve, do I know the answer to this subproblem? And the way we achieve this is with a cache. Whenever you see DP tables, dynamic programming tables, every single cell in the cache indicates a subproblem. Have I answered this subproblem? So what we need to realize is if we already know the answer, we don't want to explore the whole subtree for 5 if we've already answered 5. It's answered right there. We don't want to explore the whole subtree for 4 if 4 is answered there. This guy is going to return. This one is going to return. And then that 0 is going to return. And then the answer to the subproblem of 2, we already understand it. It'll be in the cache, somewhere in memory on the heap. Subproblem with 2, checked. It's answered. This guy's going to return, and then he's going to go right. That's a base case. Base case knows what it is. It knows it's the answer. It returns. Subproblem with 3, it's solved. And then the 3 returns to the 4. And then this 4, I truncated the tree. It would go to its right. And it would subtract 2. The subproblem would be 2. But we already know 2. It would immediately chop off that tree of recursion, and we would return. This would essentially become a base case because it would become knowledge. It would become already understood knowledge. Our base cases are assumptions that this is how the recursion will end. And now we know the answer to the subproblem of 4. And then 4 is going to return to 5. 5 is going to go down right. But what happens? 3 already knows this answer. Do you see these guys down here? None of this will get executed. 3 will just know the answer. It'll return. And then we have an answer for 5. And then 5 will return. And then 6 will look to its right. And then 4 is already answered. None of these subtrees will execute, so they're going to disappear. And then 4 is just going to return its answer. And then we're going to return to 7. 6 now has the subproblem solved. 7 is going to go to the right. And think about how many calls we just saved here. By not recomputing the 5, we basically saved half a tree of calls. This won't happen. 5 will just return, and then we are going to return the answer to our caller. And this is what memoization is all about. It's all about caching your values and eliminating recursive subtrees. If we can eliminate subtrees, we change the time complexity. And remember our reasoning before. Our reasoning before was our branching factor is 2, and our depth is n. So our time complexity is going to be upper bounded roughly to 2 to the n. Our branching factor, to the n. Why did we say that? We said that because we did the math and we found in a perfect tree with a branching factor of 2 and a depth of n, if we're doing constant time in each call, which we are doing constant time, we're going to have at maximum an upper bound of 2 to the n calls. We're upper bounding the calls. But notice how many calls we are going to have here. We might not be able to get an exact amount, but we notice a pattern. There are n subproblems. Notice how we're going 7, 6, 5, 4, 3, 2. There are n subproblems. We're going to spend a constant amount of time computing each one. As soon as we finish n calls, which are each constant time, so far we can upper bound to linear time, what is going to happen is we'll return to this 2, and then the 2 will know the answer in constant time. 3 will know the answer in constant time. 4 will know the answer to its right subtree in constant time. 5 will know the answer in constant time. 6 will know the answer to 4 in constant time. And 7 will know the answer to 5 in constant time. So what work did we actually do? We're doing a linear amount of work here. The reason being is the depth of our tree is the farthest we go. All other subproblems are answered by that point, and they're going to be constant time checks. So when we made our blanket bound of 2 to the n, we assumed this tree is going to turn into a perfect tree, a big tree. But in reality, we turned this into almost a linked list with some little forkings coming off that are constant time checks. Otherwise, it's a linear amount of work. If the input size were to scale very, very large, we would be able to bound to some arbitrary multiple of a linear function, which just turns into linear time. This is exactly what memoization will do to functions that have a branching factor to an exponent. Often you're going to see the exponent drop down. And when the exponent drops down, it's a huge save in time. 2 to the n versus linear time is an extreme improvement. So let's go back to our Fibonacci function, refactor it to implement some caching. Okay, so I just put this implementation up. I hope it's not off by 1 in terms of indexing. We want to rely on our cache and our understanding of previous subproblems to speed up our algorithm instead of recomputing naively over and over. What we can create is a cache, it can just be a simple array. It could be a 2D matrix. The shape of the cache depends on the subproblem. In this case, the subproblem can be mapped to a one-dimensional array. It's just from 0 to this number, what is the sum of the Fibonacci sequence between them. That is the subproblem. It can be modeled by an array. But we see other problems where the subproblems can be modeled by 2 independent variables that rely on each other, like a certain amount of coins existing versus a certain amount. That's going to give us a 2D matrix because the subproblems decompose differently and relate differently. But sticking to this problem, we create a cache, we call an auxiliary function, and we have the cache. This is somewhere in the heap. We have access to it through all of our recursive calls as long as we pass the reference along. And then we have our base cases in normal, that's normal. Where we change is this code right here. I hope that the indexing is right, but we have the cache being accessed at n, where we're asking ourselves, do I already have an answer for this subproblem at n? That's what this is asking us, asking the cache first. If it equals 0, arrays in Java are initialized to 0 by default, primitive integer arrays, and if it's 0, that means we haven't solved the subproblem. Solve the subproblem, store that in the cache, and then return the answer from the cache. Now, in memory, the cache has all our answers like before, we saw it over here, and our algorithm is going to now run to linear time. We're going to spend more space, but that's fine. It's better to save time than to save space because we always can make more space but not more time. So those are the fundamentals of memoization. You're going to see this pattern of having a cache right after the base cases. The base cases understand the answer. The cache already might have pre-computed subproblems, business logic, and then we ultimately return. This is the pattern you'll see with memoization, and it's something you can apply to problems that have subproblems to them.